Good afternoon, everyone. Welcome to the Joint Mathematics Meetings 2018. I'm Deanna Hansberger, President of the Mathematical Association of America. We have a very exciting program in store for you at JMM this year, and this is the first invited speaker of the MAA program. It's my pleasure to introduce Alissa Kranz, Professor of Mathematics at Loyola Marymount University. In fact, it's an especially great pleasure, as I have known Professor Kranz for nearly 21 years now, since her undergraduate days at the University of Redlands. At that time, she participated in the Carleton Summer Mathematics Program for Women. She understood what we were trying to do in SMP, and she quickly transitioned from a student in the program to taking on a leadership role in our community of math women. For those of you who know Professor Kranz already, you won't be a bit surprised. She has taken on a number of leadership roles and positions which are organized around building community and welcoming others into mathematics. She has been involved in the Carleton SMP for Women ever since 1999, including being a TA several times and being one of the organizers of the Graduate Education Mentoring Workshop for 8 years. She has been an EDGE instructor several times. She has been an instructor at the Summer Program for Women in Mathematics at George Washington University. She is the co-recipient of the AMS's Programs That Make a Difference Award for her role in co-creating and co-running the Pacific Coast Undergraduate Math Conference. She was the Associate Director of Diversity and Education at MSRI, and now she's the Associate Director of MAA's Project Next. She is also a gifted expositor, earning the Merton Hasse Prize for a noteworthy expository paper in an MAA publication, and a gifted teacher, earning an Alder Award for distinguished teaching by a beginning college or university mathematics faculty member. Professor Kranz's research is in the field of higher dimensional algebra, and she investigates categorifying algebraic structures called quandles, with the goal of defining new knot and knotted surface invariants. Her talk today is called Quintessential Quandle Queries. Join me in welcoming Professor Kranz.
Thank you all for being here, and thank you to Deanna for the very kind introduction. I'd also like to thank the MAA for the opportunity and the honor of being here today. Some of you may remember when Jay Leno was the host of The Tonight Show, and he had this sketch that he'd go out on the street and he'd ask people questions. He called this jaywalking. I decided that I wanted to do the same thing with the notion of a quandle. So, I didn't go out into the general public. I asked a bunch of math friends and some non-math friends as well. A good friend of mine pointed out that really what we were doing here is playing the mathematical version of balderdash. And the responses I got were the following. So you'll see that the words that are larger than others were the ones that appeared more times. A very close friend of mine pointed out that when he voted for a quantum bundle, he said, a fiber bundle that you only know its properties probabilistically. If you take all of the phrases here and instead just look at the words that show up, notice that we have some other fairly large words, candle and ducks. So I'm sorry to say that I don't have any quantum candles for you or bundles of ducks today, but we'll still talk about this notion of what a quandle is. Okay, so let's start at the beginning. So Takasaki, fresh new Japanese PhD living in China in the early 1940s, he's interested in looking at geometric symmetries. So in particular, he's interested in the algebraic structure that results from the notation, or from the idea of a reflection. So he wanted to define some sort of distributive algebraic structure to capture the notion of reflection in the context of finite geometry, in comparison with symmetric spaces in differential geometry. So he considered the plane, and what we're going to do is we're going to rotate one point around another. And that's what this operation is called. This is what he referred to this operation as. He also looked at another example. He was considering the reflections of an n-gon. So in this particular example of a triangle, we see that if we use this operation, if we let 0 act on 1, we get 2. 1 acting on 2, we get 0, and so on. About 20 years later, we have 2 bored undergraduates in the UK. They were curious about what happens when you start with the notion of a group, discard the group multiplication, so that only the notion of conjugacy remained. So they were interested in an operation of this form, this AB A inverse, and what structure resulted when you looked at groups with only that operation. If we look at the symmetric group S3 with this operation, we see that we get this table here, and as you're staring at that, it's not a group table. Okay, so there's some other structure going on here. Again, another 20 years later, we have Matveyev, and he was looking at a structure of taking a group and an automorphism of that group and defining this operation here. So again, if we use our example of S3, and we use this automorphism that leaves the 3 cycles alone, we'll get a different operation table here. So this is different from the one that Conway and Wraith were considering. Again, not a table of a group. Okay, so in roughly the same year that Matveyev was looking at these examples, on the other side of the Iron Curtain, we have David Joyce, who is also looking at these sort of structures, the same ones that Takasaki, Conway, Wraith, and Matveyev were looking at. And it's because of Joyce that we have this word quandle. So here's the definition of a quandle. What this is doing is this is taking the examples that we've seen before and coming up with the definition that explains what's going on in all of them. For those of you who work in this area, I can already hear you groaning. I know that my choice of notation for this afternoon agrees with roughly 23% of you. A quick survey of recent articles on the archive show that my notation is the least popular notation. So I apologize for that, but this is what I have chosen, so this is what we will be using today. For those of you who are not in this area, the reason why this joke was funny to others is because there are many different notations out there. Instead of using triangles, some people use a star, some people use some people use exponentiation, some use a triangle pointing the other way, some use an action happening on the other side. So there are many possible combinations of notation that we could have, and this is the one that we'll be using today. Let's look at these laws here. I have lots of comments about them. The first is we don't have an identity like we do for a group. So there's no 1 for a quandle. Also, this operation is unbalanced. This is why I like the triangle notation. We should really think of this operation as being an action. So one of these elements is acting on the other. This operation in general is not commutative, and even worse, it's not associative. Okay, so we have to be careful with parentheses whenever we're writing down the terms. Okay, let's look at each of these individually. So this first axiom is an idempotence condition. Idempotence shows up in many places throughout mathematics, so this is not sort of unique or interesting for a quandle. The second axiom people refer to as an inverse axiom. And the reason why is because I can get rid of that existential quantifier at the cost of introducing another operation. So I'm going to introduce the operation of triangle inverse. And how does it get along with triangle? Well, it acts like an inverse. It turns out that the triangle inverse satisfies the 3 quandle axioms as well. So Q together with this triangle inverse is itself a quandle. People refer to that as the dual quandle. And finally, finally, the self-distributivity axiom. This is really the star of the show. People are interested in this axiom completely independent of quandles, and I'll have more to say about that later on. Now, my very first talk about quandles was when I was a graduate student. So I had the honor of learning what these structures were from Sam Nelson, who is somewhere around, and will be speaking tomorrow. You should come hear him. But the first talk that I gave was at the summer math program at Carleton College that Deanna mentioned. And I don't know if Deanna remembers this, but after that talk, you emailed David Joyce, and you asked him where he came up with the name quandle. And he wrote her back, and this is what he said. The email went on to say this. And then a few years later, my thesis advisor, John Baez, was working on a blog posting, and he wanted to know where the word quandle came from. And I guess he had forgotten that I had this information already, so he sent an email to Joyce. And Joyce wrote back again, this was a few years later, and said this. So at least they agree, these two responses from Joyce years apart. About 7 years after Joyce's dissertation, we have Brieskorn, who was interested in similar ideas. And he gave the name automorphic set to this structure. Now, in fact, this is really the mathematically correct term for this structure that we call a quandle, but people deemed it too cumbersome, that if we were going to add additional adjectives to this word, automorphic set was already slightly too long. But the reason for the name is because the second and third quandle axioms say that the action of any element of our quandle is an automorphism of the quandle. So what I'd like to do now is I'd like to show a bunch of examples, in particular come back to these examples that we started with, but first let's talk about this notion of terminology and other folks who have contributed and independently talked about or discovered the notion of a quandle. So there were lots of names out there, lots of people involved, and again, the word quandle has sort of stuck. All right, so let's consider this example. This is not one that we've already seen. We're going to look at the plane, and we're going to let A acting on B contract B t of the way toward A. So if I draw a picture of that, we see that, again, if we contract A down towards C, toward B, and then B towards C, we get these dots here. And now let's verify the self-distributivity axiom. So I need to introduce a new line here, and that's going to get us one side of the self-distributive axiom. And now I need to draw this other line, and because of similarity, we get that these are equal to each other. Let's go back to some of these examples that we started with. So Takasaki's reflection quandle. Remember, we're taking B and we're going to rotate it pi radians about A. Let's verify the self-distributive axiom. Okay, so let's reflect B about A. Now let's reflect B about C. And A about C. And now we have two more reflections to make in order to get the self-distributive axiom. So we'll take A acting on B, we'll send that over C. And then we'll do the final one over on the right vertical line to get the other side of the self-distributivity axiom. This reflection example can be generalized by replacing the plane by any geometry with point symmetries, satisfying some general conditions. So for example, we can put a quandle structure on the sphere or the real projective plane. Let's also look at Takasaki's other example. Okay, remember what happens here is it 0 acts on 1 to give us 2, 1 acts on 2 to give us 0. And so we get this quandle table in the upper right. My rows are acting on my columns in the table. And the name for this quandle is D3. This is the dihedral quandle. So there's a family of dihedral quandles. We'll talk about them a little bit more later on. The general construction for a dihedral quandle is to start with Zn and make this definition here. Again, remember what's going on here. We're capturing the notion of reflection in the context of finite geometry. Let's go back to our Conway and Wraith examples. So remember, they were looking at the wreckage left behind when we start with a group, discard the group multiplication, and only consider the notion of conjugacy. This conjugation quandle is really the quintessential quandle. The axioms of a quandle precisely capture the essential properties of conjugation in a group. We call this quandle the conj quandle. That's the conjugation quandle of S3. And let's look at this quandle a bit more carefully. Let's look at its table. We see that we can write conj as a sum of these components. So why are these components and not just subquandles? So there's no way to get from any one of these blocks to any of the other blocks using any element of the quandle. Okay? So we say that this quandle is not connected. And let's look at these 3 components. So we have this gray identity quandle together with our dihedral quandle from Takasaki, the previous example, and then this pink identity quandle. So what's happening here is that the gray one is acting trivially on both the other blocks. The pink one, the pink identity quandle, rotates the 3 elements of the dihedral quandle. And the dihedral quandle is going to flip the 2 elements of the pink identity quandle. So let's just talk about the conjugation quandle in general. So you've probably realized that any abelian group has the same conjugation quandle. We could have used n-fold conjugation if we would have liked. And in fact, any subset of our group that's closed under conjugation will be a subquandle. We have a functor from the category of groups to the category of quandles, and that has an adjoint functor. It goes by many names. It's the obvious thing that it needs to be. So we could write down the definition of that, but we will do that another time. And finally, the conj quandle is never connected. So remember what the components of conj are. They're the conjugacy classes. And any element of the center of our group is going to be in its own singleton component. So at the very least, we have the identity of the group in its own component. So conj will never be connected. Now, I should point out that there are many examples of quandles that don't come from conj. A very small example is this one here. So this is not the conj of any group. And another example is, well, the first time that we have 2 non-isomorphic, non-abelian groups, it turns out that their conjs are the same. Okay? So what this means is that conj isn't particularly discerning, that the conjugation structure of a group doesn't really pin down our group for us very precisely. Let's look at another construction of a quandle from a group. So this is Matveyev's example. Remember, we're starting with a group, and we're taking an automorphism of that group subject to this operation. Now, when that F is inversion, and I'll say a little bit more about that in a moment, then we call this the core quandle. Now, some of you may remember that inversion is not always an automorphism of a group. It is in the case of abelian groups, but of course S3 isn't. So it turns out that it's just this really nice fact that Matveyev's construction works either for an automorphism of a group or for inversion. So when we use inversion, what we get is this structure that we call the core quandle, where our operation is defined as A, B inverse A. If we look at this quandle, we see that it also is not connected. It has two components, and these are both the dihedral quandles, and they act trivially on one another. Okay. If we go back to Takasaki's example of this triangle and looking at reflections, it turns out that the dihedral quandle is core. So the dihedral quandle dn is the core of Zn. Just as we considered facts about the conjugation quandle, let's look at some facts about the core quandle. So core is always homogeneous. What I mean by that is that the automorphisms of core act transitively on the core quandle. And this implies that all the components of core have the same size. A nice example is that every Lie group has a symmetric space, and the associated quandle structure on that is the core of that Lie group. As in the case of conj, there are many quandles that are not the core of some group. In fact, this example that we just considered that wasn't the conj of anything, this also isn't the core of anything. So just so you know, this is the only other non-trivial quandle of order 3 besides our dihedral quandle that we've already been talking about. Joyce showed that there was a quandle structure on the sphere and also the hyperbolic plane, and that neither of those are the core of anything either. Okay, so there are many examples of quandles that don't come from conj or from core. Finding two groups that had the same core was a bit more work. One is commutative, one isn't, so this semi-direct product is given by that rule there. Let's go back to this example of Matveyev, where we were looking at S3 together with this automorphism that left the 3 cycles alone. Now, this quandle is homogeneous. Again, that means that the automorphisms of it act transitively on it. We see that it has 2 components. They're both these identity quandles. And each of these 3 eyes rotates the 3 elements of the other one. Now, this quandle turns out to have some very nice properties that we're going to talk about. And the first nice property that it has is that it's medial. So what does mediality mean? It means that it satisfies this funny rule here. Now, why should we care about this property of being medial? Well, I sort of was groomed mathematically as a grad student as a category theorist, a little bit. And so whenever I learn about a new algebraic structure, my first question is about the morphisms between them. And in thinking about other algebraic structures that we know, it's this very nice fact that the collection of linear transformations from one vector space to another has a vector space structure. But the same isn't true for groups. Now, we're slightly less irritated when our groups are abelian. And so the natural question to ask is, what about our quandle homomorphisms? When, if ever, is it the case that the set of quandle homomorphisms admits a quandle structure? So in some joint work with Sam Nelson, we showed that what we need is precisely this notion of mediality. We need the target quandle to be medial in order for the collection of homomorphisms to have a quandle structure. So what this lets us do is go back to these examples that we've been talking about, and we can hom into this super nice quandle. So starring in the role of X is this quandle whose table is over on the right. This is the one from Matveyev where we use S3 together with that automorphism F that left the 3 cycles alone. We're going to take conj and core, and we're going to hom into this quandle here. And if we count the number of homomorphisms, this is what we get. Now, as I mentioned, this quandle, this Matveyev example of S3 together with this F that leaves the 3 cycles alone, it's got really, really nice properties. So another nice property that it has is being 2 reductive. That means it satisfies this axiom here. So let's go back to these examples that we were looking at. So again, we're homming the conj of S3 into this really nice quandle, the core of S3 into this really nice quandle. And we remember that conj core and this nice one, none of them were connected, and these are their components here. Well, let's see if we can figure out where some of these numbers are coming from. So those red numbers, the 3s, those are the size of the components of our target quandle. Okay? This really nice quandle, this target quandle X, is homogeneous. So that means that its components have the same size. So that's where this 3 is coming from. And then the blue numbers, the blue 3 and the blue 2, where are those coming from? Those are the number of components of our source quandle. And it turns out this is no accident. Okay, so the result is when the target quandle is medial, 2 reductive, and homogeneous, then we know the number of homomorphisms from Q into X. This is joint work from this fall together with my collaborators Marco and David. So coming soon to the archive near you. And moreover, we know more. We know about the structure of this Hom quandle. It turns out to have a product structure. It's a subquandle of a product of copies of X. How many copies of X? Well, it's the number of components in the source quandle. Okay, so we can completely describe what this looks like. Now, I know what you're thinking. You're thinking, sheesh, there's a bunch of hypotheses here. When does this ever hold? She just found some really nice examples for this talk. Oh, no, it happens far more often than you might think. This table gives us the number of medial quandles and the number of medial and 2 reductive quandles. And when I met David in the fall, he told me that he, together with some of his colleagues from Prague, have shown that the fraction of medial to all quandles and also the fraction of medial and 2 reductive to all quandles, these go to 1. Okay, so there are lots of these quandles that satisfy the hypotheses of this result. The one guy that's not medial of order 4 is this one here. And notice that it has components I plus D3, this dihedral quandle showing up again. Okay, so I mentioned that the self-distributivity axiom was of interest to lots of people in a lot of different fields. It turns out that a set together with an operation that satisfies the self-distributivity axiom is a very rich structure. So there are many people interested in connections between quandles and things that they're interested in. So for example, something that is completely not obvious is that if you have a set and an operation that satisfies the self-distributivity axiom, and you equip that with some sort of unit, so an element 1 that satisfies this law here, it turns out that that gives an associativity. Okay? Unexpected. There are lots of people interested in this and, in fact, studying sort of a cohomology theory of these structures. There's also a notion of cohomology of quandles. There are people relating those to other known cohomology theories. Turns out that there's an application to cryptography. So there's an authentication scheme from the self-distributivity axiom. People interested in set theory are interested in these self-distributivity axiom structures. There are connections to cross modules and categorical groups. And of course, anyone studying any sort of non-associative algebra or non-associative structure, like Mufang loops or Leibniz algebras. They're interested in connections between those and quandles. Okay. In fact, this is a photo from a conference in Denver this past August, where a bunch of non-associative algebra people showed up, and we were chatting about all of these ideas and how they're related to one another. So I know what some of you are thinking, well, but she forgot to talk about the bridge to a whole other area of mathematics that quandles show up in. And you're right. There's a relationship between quandles and knot theory. So let's switch a little bit from talking about the quandles algebraically to talking about them more topologically. I know many of you know this, but a knot is just a knotted loop of string where we join the edges together, the ends together. Colin Adams does this really great thing that he uses, a cord or a cable that can fit into itself to give a nice illustration of this. We say that two knots are the same or that they're equivalent if I can wiggle one and obtain the other without doing anything severe, like cutting it or passing it through itself or something like that. So here's an example. Okay, so the knot we started with in this one are the same. Now in the 1920s, we have Kurt Reidemeister, who introduced what we now call the Reidemeister moves and gave us a convenient way to determine whether two knots are the same. We can just see whether or not there's a finite sequence of these moves that transform one of these knots into the other. Now I know many of you are familiar with these moves, but let's look at them individually. So the first Reidemeister move involves one strand. It tells us we can add or remove a kink from our knot without affecting anything. The second Reidemeister move involves two strands. It says that I can pull the two apart on the right, or I can introduce that crossing. And finally, the third Reidemeister move, some like to refer to this as a crossing of crossings. I can take that third strand and I can slide it over the crossing up there. Now I know what you're all thinking. There are three Reidemeister moves. There were three quandle axioms. If something is right with mathematics, there must be some sort of connection. And indeed, you're right. So in order to illustrate that for you, we need to come up with some conventions for how we're going to color our strands. And so notice that my overstrand is acting on my understrand, and which way we're acting depends upon the direction of the crossing here. Okay, so let's start with the first Reidemeister move and see how it corresponds to the first quandle axiom. So we'll label our strands, and we know that because we only have one strand, that thing over on the right had better be A. So now when we use our convention, we see that this is A acting on itself, and thankfully that's the first quandle axiom, so we're okay. If we look at the second Reidemeister move, now we have to use both of our crossings. Let's first deal with the overstrands. So the overstrands just carry down and they maintain their same name. Now let's look at the top crossing on the right-hand side. We see that that's going to be A inversely acting on B. And now A, the overstrand, is going to act on that. And we know that the triangle and the triangle inverse, they're inverses of each other. This is the second quandle axiom. That gives us B. Finally, the third Reidemeister move, this one's the most exciting. So again, let's deal with the overstrands first. Now let's look at the second strand B and see what happens to that. So notice that on the left side, B is the overstrand, and then it comes into the crossing with C, so C is going to act on it. Over on the right, C acted on it first and then became the overstrand. And now finally, the third strand here is going to give us the self-distributivity axiom. So on the left side, we have that B, the overstrand, acted on A, and then C, the overstrand, acted on that. Over on the right side, we first have C, the overstrand, acting on B, C, the overstrand, acting on A, and then C acting on B is the overstrand, which acts on C acting on A. So this reveals for us the third quandle axiom. And so what we're seeing is that the quandle axioms are just algebraically encoding the three Reidemeister moves. And so some of you may be familiar with the fact that it's because of this that the quandles provide a solution to the Yang-Baxter equation. Okay. So now let's see what other connections we have to knots. So let's consider this figure 8 knot. And we're going to color it with 4 colorings, which we know we can do. Each arc has its own color. And it turns out that there's a quandle structure on these colors that we've used. So in order to determine that quandle, we're going to remember what our conventions are. But that rule over on the right, let's not use the inverse triangle. So what I'm going to do is I'm going to apply A to both labels of that understrand. So when I do that, we get this here, which is equivalent. So we're going to use this instead. All right, so if we want to fill out a quandle table for the quandle of colors of this knot, we know that we, for free, get the diagonal from the first quandle axiom. And now what we're going to do is we're going to look at the crossings. And so for each of the crossings, we'll read off a rule according to our convention and fill in the table. So the upper left crossing there, we see that 1 is going over 0. It's the left convention, so we get 1 acting on 0 is 3. And again, in my table, I'm letting my rows act on my columns, so we're filling in that yellow square right there. Let's move now to that bottom crossing, and we see that we have 0, the black strand, acting on 1, the red strand. That gives us the green strand 2. Now this middle crossing, we have the overstrand 3, the blue strand, acting on 2. Oh, I'm sorry, acting on 0, based off of our convention over on the right. And finally, this bottom crossing, again, we have the convention on the right. And so we can fill in 2 acting on 1, gives us 3. Okay. So this is all we get from the first quandle axiom and using our crossings. Now what we need to do is we need to fill in the rest of this table. So let's look at this bottom square here, 3 acting on 1. Using the self-distributivity axiom together with the second quandle axiom, and knowing that we only have 4 colors here, we can determine that that entry is 0. Now we could keep going this way. We could keep filling in the other squares using the axioms of a quandle, or we can use a shortcut and recognize that that second column there tells us that this quandle is connected. And it turns out, fortunately for us, there's only one quandle, connected quandle of order 4, and here it is. So this quandle has an especially nice representation as the action of rotations of the tetrahedron on its vertices. Okay? So let's imagine that I'm going to let the black vertex act on or operate on the red vertex. So what I'm going to do is I'm going to rotate this a third of the way clockwise and see where it goes. And so if we watch that here, we see that, as expected, 0, when the black one acted on the red one, it took us to where the green was. Okay. We could also, as another example, let's let the red ball act on the black one. So again, what I'm going to do is I'm going to rotate this a third of a turn clockwise. And so what happened is that the black went to where the blue was. And that video here shows that as we expected. Now, I would have shown you the analogous quandle structure on the icosahedron, but the model for that just didn't fit in my two-door Civic, so you were stuck with the tetrahedron. Now, just as we have the notion of a fundamental group of a knot, we have the notion of a fundamental quandle of a knot. And I'm going to introduce this in terms of its generators and relations. So the arcs are exactly the things that we had colored in our previous example. This time we're going to label our arcs by the letters A, B, C, and so on. So let's go back and look at our figure 8 example. We're going to label our arcs with these letters. These are going to be the generators of our fundamental quandle. Now to get the relations, what we're going to do is we'll read them off at the crossings, just as we did before, according to these conventions that we have. So when we look at the figure 8 and we look at these conventions, when we go to each of these crossings, we read off a relation. And so what we wind up with is this structure here. We have these 4 generators and 4 relations. So remember what this is. This is the free quandle generated by these 4 generators, A, B, C, and D, which means I can freely form the quandle words that I want using the quandle axioms, and then also subject to these relations here. Now, at first, people thought that this was a presentation of a group, but then they realized that the relations only involved conjugation. So they realized that what we had here was actually a more general structure. Now, the fundamental quandle of a knot is infinite, so that makes it slightly difficult to work with. And so instead, what we often do is we look at quandle homomorphisms from the fundamental quandle to some finite quandle of our choice. This is why I was very interested in this question of Hom quandles that we were talking about earlier. Now, I know what you might be thinking. Well, didn't we just do this? Didn't we just look at these crossings and use the same relations, and we wound up with this finite quandle here, this finite 4-element quandle? Well, to some extent, you're right. So a coloring, which is what we did, that's precisely a quandle homomorphism from the fundamental quandle into this 4-element quandle. Now, there are multiple colorings of the figure 8 by our 4-element quandle. Ours is just one of them. And obviously, we have more homomorphism. There exist more homomorphisms from this fundamental quandle into our quandle here. Okay, so we just have one of them here. So Joyce and Matveyev independently showed that the number of colorings of a knot by the elements of the quandle is precisely the number of quandle homomorphisms from our fundamental quandle to our chosen quandle. And it turns out this number is an invariant of knots. This is something that's nice and generally easy to compute. It allows us, for example, to distinguish the trefoil from the figure 8, which, of course, we already knew were different. An even more powerful result, though, Joyce and Matveyev independently showed that the fundamental quandle is a much stronger invariant than the knot group of a knot. Okay? So it's a complete invariant up to orientation and mirror image. So in closing, I'd like to thank a bunch of people who are responsible for teaching me everything that I know about quandles. They are all in this picture, so Sam, Yosef, Masahiko, and Scott. And if you're wondering where can you learn more about quandles, well, these are the 8 most recent papers on the archive, so I encourage you to go look at papers on the archive. Another option is there are these 2 books, one by Springer, the other by the AMS. I also encourage you to look at Joyce's thesis. There's been some nice articles in the AMS notices, and on occasion there are blog posts or columns about quandles on various MAA and AMS sites. But But even better, I encourage you to come to our session tomorrow. So we have a session about quandles tomorrow that starts at 1. Will be led off by Sam Nelson. And there are a bunch of folks in the audience here who will also be speaking. And their work is very related to what I've been talking about thus far. So thank you all very much, and I hope to see you tomorrow.
Thank you very much, Alissa. Are there any questions? We have a few minutes. Yes.
So I was going to ask you,
Sorry.
the quandle structure could tell a left-handed trefoil from a right-handed trefoil, but you're saying no, it can't do that.
Right. Is that correct? Those of you who just making sure? Yeah. There's no identity element. Correct.
Yes.
Do you also get a complete invariant for links?
No, the if and only if works one direction. I believe it works that if the two links are isomorphic, then the quandles are isomorphic, but not the other way.
Professor Cranes will continue to be up here for a minute or two. If you have other questions, come on up. But once again, let's thank her for a most enjoyable talk.